One of the most asked questions around the world is, what is inside a black hole? Black holes are some of the strangest and most fascinating objects in space. Literally nothing can escape the black hole once it gets close to one, because the gravity surrounding the black hole is so intense that it wraps not just space and time, but also light and information. Black holes are the most fascinating cosmic phenomenon due to this mystery. According to current theories, the inside of a black hole is a location where matter is compressed to an endlessly small point and where all concepts of time and space and our knowledge of physics dissolve into it. In this video, we'll try to understand what scientists found out about the black holes. Make sure you stay tuned to the end of the video to know more about these scary giant entities. Before we begin, welcome to Discover Space. If you want to be a part of our space journey, don't forget to click the subscribe button and hit the notification bell next to it to be the first to know whenever we upload a new video. We now have a good idea what happens outside of a black hole thanks to a powerful telescope and our knowledge of universal physics. Thanks to geniuses like Albert Einstein and Stephen Hawking, black holes have three layers: the outer and inner event horizon, and the singularity. A black hole's event horizon is the area surrounding its mouth beyond which light cannot travel. A particle cannot depart the event horizon once it crosses the event horizon. Across the event horizon, gravity remains constant. The singularity, or one point in space-time, where the mass of the black hole is concentrated, is the area inside a black hole where the object's mass is located. Black holes are invisible to scientists, unlike stars and other celestial objects. Instead, astronomers have to detect the radiation black holes release as gas and dust are sucked into the massive objects. However, because of the dense gas and dust that surround them, supermassive black holes that are at the galactic center may get obscuring their telltale emissions. Sometimes, instead of being pulled into the black hole's mouth as matter is attracted towards it, matter ricochets off the event horizon and is flung away. It produces bright jets of matter moving at nearly relative speeds. These strong jets can be observed from a vast distance, despite the fact that the black hole itself is not visible. We also know that light gets trapped inside the gravity of a black hole because the escape speed is faster than the speed of light. Here, space and time are difficult to differentiate from one another. Physics forgets its laws and everything is pulled inward. We don't know what takes place in the singularity. But thanks to the capability of quantum computers, we now have some brand new, totally unexpected information about the nature of these always hungry giants that are the center of nearly every galaxy we are aware of. What if I told you that a recent study indicates that the universe's scariest entities are merely illusions? No, their existence is not being denied here. Recently, the research team from the University of Michigan put out a more comprehensive idea on the interiors of black holes. The simulations conducted by the research team, led by Enrico Rinaldi, suggest that the black holes are really holograms. No, not the holograms you see in science fiction films. Instead, the term hologram is used in this context in a more scientific manner. Its foundation is the mathematical conjuncture of holographic duality that attempts to connect theories of particles and their interactions with the theory of gravity. In simple words, it all boils down to the absence of a single comprehensive theory that might explain the universe as a whole. While the standard model of physics deals with particles and completely overlooks gravity, Einstein's general relative theory asserts that there are no particles, only space-time, so deals in the third dimension. As a result, it is described in the second dimension. Both of these theories can be used to explain how black holes function, but physics has struggled for decades to find a point of agreement between the two competing theories. In this regard, Rinaldi and his team may have been successful. Using all they know about the theory of particles and the theory of gravity, they integrated the two theories and used quantum matrix models to investigate holographic duality. The plan was to use simple matrices composed of blocks of numbers. From there, they may use a framework found in quantum computers to begin and create things. The researchers were able to describe how the gravity inside a black hole may appear to be running the simulations with the models built in the framework. Our present understanding of a black hole's interior is essentially based on the theory of gravity. This implies that space-time enters and exits a black hole from the outside. But this is where things become tricky. Space-time calculations within a black hole are not as accurate as those outside one. We lack information about what occurs inside a black hole. Therefore, we must solely rely on mathematical computations for the purpose of our research. These calculations, from Rinaldi's perspective, demonstrate that it is better to think of a black hole's internal workings as being similar to a holographic projection. Surprising, right? Let's define a hologram in this context first, though. In this context, a black hole is a flat image or a two-dimensional image that is capable of being projected in 3 dimensions. Researchers were able to define a black hole as an object with a 3-dimensional structure, but we see it via the 2-dimensional particles by using the quantum matrix models to study the relationship between the theory of gravity and particle theory. Although this description is based on the most recent calculations, it is still merely a mathematical representation. This indicates that it is still only a space theory. Scientists have attempted to predict the interior of a black hole using mathematical equations before. In another special mathematical instance, astrophysicists have deduced that the singularity inside the black hole is actually a ring and not a point. According to the Kerr metric, the geometry of a rotating black hole is defined by the centrifugal force that causes the horizon of the black hole to bulge out into an ellipse. The singularity is transformed into a ring by the same centrifugal force. The ring singularity is the focal point of confocal ellipsoids formed by the outer and inner horizon. But in real life, the mathematical circumstance won't happen. Other calculations in the past suggested that the event horizon's event singularity is truly a complete surface. We simply are unaware. It's possible that singularities don't even exist in actual black holes. Another theory contends that matter does not compress into the infinitely small point known as a singularity deep inside a black hole. Instead, it might exist as the smallest volume pocket that is also potentially the smallest configuration of matter. This theoretical possibility is envisioned by a loop quantum gravity, which is a widely speculative idea for producing a quantum force of gravity. This would be a Planck star. The cosmos around us is made up of little discrete chunks in the loop quantum gravity universe, yet at such low scale that our movements appear smooth and continuous. We won't be able to know for certain if what we are seeing is all there is to see in 2D, 3D, or beyond until we figure out a technique to retrieve data from the interior of a black hole. If the most recent predictions are correct, the existential question, if the black holes are a hologram, what about the rest of the universe, arises. There isn't a definite answer at the present. As of now, we know the actual universe is a 4-dimensional system with volume and extends in time. If our universe had holographic physics, there would be a different set of physical laws that operate on a 3D space-time border, somewhere that would be equal to our current understanding of 4D physics. And as of right now, we are not aware of any such 3D theory. Holograms are, of course, only 2-dimensional images produced by lights in a 3-dimensional environment to us. However, in this instance, Rinaldi and his team are talking about how a black hole interacts with its surroundings. On the other hand, the universe presents a unique situation. Black holes depict the point at which relativity and quantum physics intersect and our universe collapse in on itself. The unifying theory that will define the universe may be found if we merely connect the two movements. A black hole may contain the answer, but it is not possible to enter one. Or is it? That's all for this video. Thanks for watching the video. If you enjoyed, don't forget to like, also subscribe to the channel and hit the bell icon to never miss a new video. Also, let us know what you think about black holes in the comments section. Until next time.